Hello again, folks. Today we're going to be covering section 2.2, linear equations in one variable. Here's a quick look at the calendar just to verify. Alright, this video is for Wednesday, the 18th of May, so we'll be covering section 2.2 per the schedule. The packet that I have for you today consists of these pages. This is hefty. There's I think maybe 10 sheets in here. Anyhow, this is firstly an overview. The sort of peculiar way the textbook is arranged, it grouped these types of equations together, so we're going to cover those two. I'm going to basically develop this diagram over the course of a couple of days, because eventually we're going to get to this and then those things. But this is an overview for today. This is more or less a reference. I had made this for a different class, but it's useful information. When we get to rational equations, we're going to need to look for lowest common denominator, which is the least common multiple. So these are methods for that purpose. You could also get your calculator to give you the number at least. Then there's sort of a worksheet. There's sort of labels that I want to fill in with you. I think it will make you remember it better. But these are situations that may arise while in the course of solving equations. This is just a reminder of different methods of factoring. That'll be more important when we get to quadratics, I think. This is an overview I made of different methods for graphing. Being that you have a graphing calculator for this class, if you want to draw the equation of a line, if you have the line, you could utilize it for that purpose. It's just two buttons basically to get it to draw something. The method that will be practical for our purposes today would basically be the slope-intercept form of the line equation. As long as you can identify what the slope is and what the y-intercept is, you're fine. All right, but there are other slightly more brute force methods, if you will. All right. This is an overview of different slopes and the slope formula. It's upside down. I don't know why I did that. Okay. I'll have to check my staple out. Here's another blank coordinate plane prepped. These are an overview of different incarnations, if you will, of the line equation. Essentially, there's the general form, which is you have everything interesting piled onto the left side of equals and 0 on the right side. Then there's, depending upon the type of problem, slightly more practical form, standard form, is when you have your x's and y's on the same side. And then there's the slope-intercept form, when the x's and y's are on opposite side. And then there's something known as the point-slope formula. All right? Basically, you could convert any form of this into any other. All right? Just beware, the labels change. All right? The reason I made this in colors so that you see these a blue x in this case and a red y is that that's the one thing that is consistently the same in any one of these. If you notice that there in some cases there is a capital letter versus a lowercase letter, or the inclusion of an M or a B that's for a different purpose, that is just subscribing a job, purpose to these parts, these coefficients and constants. All right, just realize you have a lot of power. All right, what's relevant to us today is that we would be basically using these two. All right, and this is how the line equation would look depending upon whether you have a diagonal line, a horizontal line, or a vertical line. This is an older diagram, which I think is a little not necessary in this case, but I included it just because of the visual aids. What's more important is the newer version of this, which is I made today. This is a summary of two line relationships. Basically, what we're interested in is what is perpendicular and what is parallel. Okay, so if you're following along, please print these out and then you can add notes to them and tape, and we'll get started. I think I have that. Okay. All right. This is a little bit of a review quickly. It's getting towards the late evening here, so I'm going to have to put the light on, I think. I don't know if this will make things better or worse. If I spin this around, I don't want to cast a shadow, unfortunately. I have to stand where I'm standing. So no, it doesn't seem to help. Okay. Let's leave that. Alright. Leave it like that for now. You know what? I'm going to put on my kitchen light instead. I think that will suffice. You may see the reflection of my fan here. But please excuse that. Anyhow, the way that this is again organized, section 2.2, is that it kind of compressed together a lot of different things. Firstly, linear equations that you solve in one variable. Linear equations in one variable, if you were to have a model for them, they would basically look something like this. This is a model that is just a general sort of skeleton that you could, you know, add a number here or there to make unique to your problem. What is key is the degree. All right. So if x is often the variable, all right, you would pay attention to specifically the degree. If the degree is 1, it's one of those things that math people tend not to bother writing. It's understood as being there. All right. So if you don't see an exponent, all right, assume it is degree 1, so it's linear. All right. Now, that means that we have to consider, all right, well, what are the techniques of solving linear equations? Because it does get progressively more involved. These are the basic type, right? If you have an equation, think about it this way, all right? An equation is more or less a building, all right? And expressions, the slightly less complicated thing, is the building block. So if you have an expression on one side of equals and you have an expression or whatever on the right side of equals, right? It's really the whole thing, all right? That is an equation per se. All right? And there's some terminology in English that would be good to know, all right? We sort of use in ordinary conversation the word simplify and solve interchangeably, but we shouldn't, because we're in math world, remember, we have to be very precise. So when you see the instruction for simplifying, just realize that that's pertaining to arithmetic per se, all right? It's pretty much what you see is what you get. If it says add, you add. If it says subtract, you subtract, all right? When you are dealing with algebra, you solve, all right? And solving algebraic equations often involves the opposite operation, so it's exactly the opposite of what you would expect. Anyhow, arithmetic is the oldest form of math. You always start with that, all right? And then when that is, you've taken it as far as you can go, then you perform your algebra, all right? Here's how so, right? You essentially will simplify, right, each side of equals independently. All right, make sure to do that before you do anything else. All right, each side of equals independently. Often when I draw these myself, I put a little dash line to make it obvious that there's a left and there's a right. There's two sides that I'm dealing with. Once that is accomplished, all right, then you solve the equation, the whole thing, all right, by strategically rearranging the parts to look like this. You would like it to basically look like a letter, a variable, right, equaling just one number, right, on one side. That's the ideal situation, all right? Letter equals number, all right? You strategically rearrange the parts, all right, to make it look so, all right? Now, to get into the minutiae here, all right, how does one simplify the left and then eventually the right independently of each other? Well, that entails two things. You'd start with the order of operations. All right, please excuse my dear Aunt Sally, PEMDAS GEMS, whatever version of it that you like. Again, it's pretty much what you see is what you get, so if it says add, you're going to add, all right, you know. Failing that, all right, or, you know, in respect of that, all right, you also would employ the distributive property. That often occurs. So Well, if you can't combine anything encapsulated in the parentheses, perhaps you can make the parentheses disappear by introducing the outside coefficient to each of the elements on the inside, each of the contents. How so? Distributive property is essentially multiplying the outside by the inside. So you would employ that technique. Okay? Try order of operations is where you should start when you're dealing with an expression, i.e. just one side independently of another, right? And then if you can't make any progress with that, then you try the distributive property. Usually that's what it entails, all right? When it comes to solving, all right, the most basic technique of solving algebraically, remember, is not to follow the order of operations per se, all right, but instead do opposite operations. So in a situation like this, if you see addition, very often you end up subtracting. If you see multiplication, you end up dividing. And anything more complicated than that would also be, be opposite. So like, for example, if you had something squared, you could square root it, and so forth. At least if the purpose at that point is to strategically rearrange the parts to look like this. In that event, you're moving things over the equals. When you move things over equals, you must employ opposite operations, right? And then, of course, the golden cardinal principle of algebra is that you balance, right? That is to say, whatever you do to one side, do to both sides, right, of equals. Okay? This is probably old hat to you, but it's important to make sure that that's, pretty nailed down. All right, you do to both sides. Basically, and I am fond of saying this because it's true, all right, you can get away with murder in math world as long as you're consistent, all right? Even if it seems cuckoo that you just start, randomly multiplying a number to a left side of an equation, make sure that you do the same thing to the right side of the equation. Everything is fair and square. It's balanced, all right? It's very zen. Okay, so having said that, or having mentioned that, let's do an example. So I'm going to erase this, and then we'll eventually get to the slides. This is the plan. I put the brake finally on my wheels here, so it's not going to move too much, hopefully. Suppose that you had to do this. Right, you're going to solve. So if you see that phrase, automatically, without them being more explicit, you would know I have an equation. Ultimately, I have to employ opposite operations. I must simplify first if I can, and then play the game of algebra. Right? Second. Right? So if you solve 4 times the quantity, x minus 3 plus 12 equals 15 minus 5 times the quantity x plus 6. And hopefully that's nice and neat. Maybe if it helps to delineate what is sides here, make that a different color. Okay? Right. So I always do this. I just put a little dash line down the equals, right? I'm going to pay attention to the left side. That says we in Western society are used to doing things, reading left to right anyhow. And I'm going to zero in on this. If I obey the order of operations, which I should, to simplify, all right, first, all right, my attention should be drawn to what is in parentheses. In this case, you see you have things that are not like terms. This is a variable, and this is a number. So I can't actually combine them. And you might go, all right, well, you can make some progress if you can get rid of the parentheses at least. And the way that you would do that is employ the distributive property. Introduce the outside thing to each of the inside things, right? Then write what the alteration is. So now what you would have is 4 times x is just simply 4x. 4 times 3 is minus 12, and there is a 12 sitting here. If you want to take it further, the next thing would be, all right, well, I have a term here which is 4 times x, and I don't know what the x is, so I can't really multiply. The best that I can do is combine these things that are like terms. So my focus will now shift to here, right? And in which case they're the same exact magnitude. So there's a cancellation effect, right? Which means if you want, you can do two things. You could just simply write 4x, which I think most people probably would do, and that's cool. Or you could fill the void. It isn't really necessary to put the number 0 here, all right? But if it makes you more comfortable, then go ahead and do that, all right? Now, if I've gotten it down to just 4x, essentially, there's nothing more I could do in terms of arithmetic here. So I'm going to shift my focus onto the other side. All right, and I have the same situation. If I follow the order of operations, my attention should be drawn to what is in parentheses. And again, not like terms, I can't really make heads or tails of that, but at least I can eliminate the parentheses by distributing the outside to the inside via multiplication. Hence, what I end up in this case is the 15 that was sitting there. Negative 5 times x abbreviated is negative 5x. And then a negative 5, remember, you always group the sign immediately to the left of the number. All right? Times 6 would be minus 30. Now they're not adjacent to one another, but if you analyze this, you would do something similar to what we had before, which is combine together what you can, all right? Namely the like terms that are 15 and 30. So combine these as the signs would dictate, which is just adding or subtracting. In this case, it's subtraction, all right? And then write what the leftovers would be. All right, underneath it on the next level, if you will. My instinct, it doesn't have to be, but I like to put this over here. So minus 5x, all right, and then the outcome of positive 15 minus 30 is minus 15. Okay. Now that is simplified to the extent that it can be, and as well over here, the arithmetic is done. I'm going to now play the game of algebra, which is the process of rearranging things so that I get it letter equals number. All right. What I do is I like to draw a little table at this point, which is I'll make a big line like so, all right? And I will strategically move things with letters over to the left. It doesn't have to be that way, but I like it that way. And then therefore things without letters over to the right. And you do that just via adding or subtracting. All right. So the 0 is kind of pointless, but in theory, what you would do in this case to move something from here to there over equals would be opposite operations. Right? So just to illustrate, this would strategically cancel, it's just 0 anyway, and then you would combine it over here, whatever you get. Now in this case, it's not going to change anything, you just get minus 15 regardless. But that's the process in motion. You do the same thing with this term, even in spite of the letter. All right? I think a lot of times people innocently will take the coefficient only, but if you're adding or subtracting, and that's all that would be happening at this stage, all right, take the whole chunk, right, not just the front of it. So in this case, you will add 5x and then plop it over here strategically where it will buddy up with 4x, right? This, nobody knows what x is right now, but it doesn't matter. By sheer logic alone, something, even something mysterious, combined with its opposite sign self will strategically cancel. Right. You don't have to write anything. You could put a 0 if you like, but it would be unnecessary. And then you have this situation to deal with. This is essentially 4 plus 5, which makes this 9x equals negative 15. Right. Now, they're kind of far apart. There's no necessary gap here, really. But if it helps, all right, I'm going to put this closer together in view of the camera, hopefully. And you have this. 9x is equal to negative 15. Right? As the last step, you're going to move the coefficient of x, again, via opposite operation in order to justify going over the equals from here to here. So if it's understood that these two things pressed together are multiplied, the justification for moving it opposite would be dividing. In algebra, of course, they have a tendency to use that symbol rather than the colon with the line. Anyhow, if you did it here, you're obligated to do it there. Hands are tied. All right? There is a simplification, i.e. sort of a cancellation effect. Strategically so, and then you end up with this. Negative 15 over 9. Now that is done, except that it can be simplified at this stage, if you like. Sometimes you can't. all right? But it is the form of letter equals number, even an unsatisfying improper fraction, granted. If you know your multiplication tables by heart, and it would be good, all right, you would recognize 15 and 9 from the multiplication tables of 3, which means that they can each be simplified by dividing them by 3, and therefore, when all is said and done, this is negative 5 over 3. Believe it or not, the improper fraction, as long as it is in simplest form, is preferred in algebra. So if you get something like that, even though it's not really conducive to ordinary conversation, you don't go up to people and go, I like negative 5/3 of something. It's fine, all right, in math world, all right? Now, another thing I should say is that I'm not going to do it because it would take a lot of time, but once you get an answer, to make sure that it's legit, you could take it and put it back into the equation and see if it balances. If it does, then it's all well and good. All right. Now, let me turn on my projector, and I'll show you my, what do you call it, the diagrams I made. Okay. And I have a lot of gobbledygook to erase, so I will. Okay. This is, again, an overview of what you'll be dealing with. Some strategies depending upon the circumstances. If it is, I think I better turn off my kitchen light at this point. So let me do that. I'll just emphasize some points here. It's okay, right? Well, yeah, that's bad. All right. This is one of the handouts. It's, again, an overview that I'm going to develop over the course of a couple of days. This section 2.1, the way that this book arranged things is that it discusses linear equations and also rational equations in the same section, all right? Normally I would think it's linear, then maybe squared, quadratic, and then to slightly more complicate things, but hey, I just went through this, all right? Essentially, the techniques for dealing with things that are linear, and I put this eyeball here and not much else, just because I want to get you in the habit of how do you identify what you're dealing with exactly? Well, the degree, or in the case of absolute values, those lines that are around the variable. But if you see a degree of 1 or it isn't written at all, then you're dealing with linear equations, and therefore the techniques are the standard basic type that will always be involved somehow. Opposite operations, doing whatever you do to one side to the opposite side, balancing. If we now shift our focus over to rational, the most basic form of a rational equation, in theory, would have a negative integer, that is a whole number, sitting here in superscript, but it would be negative, all right, as the exponent, as the degree technically, all right? What you're more likely to see is the expression of that, the actual very explicit drawing of it, which is to see more or less something that looks like a glorified fraction. A ratio would be a better word for it, but an obvious top, a line, and then an obvious bottom, however complicated. Now, typically, the variable is in the denominator, all right? There is another type, all right, which I'll put up here just for reference, all right? Another type that's technically rational, just to carry this up, which is essentially the proportion equations. Proportion equations are when you have basically what looks like a fraction set equal to a fraction. It's less complicated than the type that we're going to go through. But the basic technique of here, when you have a proportion equation, is to cross multiply. So just sort of remember that for now. All right, there's a cross multiplication if you just have one simple ratio set equal to one simple ratio. If you have something more complicated than that, that there's extra terms, all right, we're going to basically employ what I've written here. All right, ideally, you're going to change the appearance of the problem that's given to you by taking advantage of what would technically be the lowest common denominator. otherwise known as the LCM, least common multiple, of the denominators, okay? That's a little bit more involved, all right? But this is technically of the rational type as well, so we'll get to an example of that. I want to talk about this first, though. Okay? Right. And even further still, if you have really ugly problems, all right, you may involve some kind of factoring. So, in some more complicated problems, you may have to factor first. Denominators essentially first, but that's a real worst case scenario. Right? All right, now I'm going to reluctantly turn this off, all right, and then give you some strategies, all right, to explain this a little bit better. All right. That's the overview. When you deal with the harder examples of rational equations, the ones that are not proportion equations per se, all right, you are basically going to change their appearance. That may sound crazy, right? But within boundaries, all right, you can legally change, mathematically legally, change the appearance of something and create an equivalent equation, all right, that is more conducive, it's easier somehow, all right? You're going to change the appearance. Now, so by basically eliminating the denominators, all right? How do you do that? You use essentially the lowest common denominator, which is also in some instances referred to as the least common multiple. All right. Okay. And I'm going to give you sort of a model. All right. I'm going to write it here. I would encourage you to write it, and I'm going to come back to it eventually. All right. Here's the model. All right. A skeleton that we will borrow and then flesh out as needed. There's enough light, hopefully. All right. All right. Essentially, there's going to be some convenient expression, right, that you're going to use, right, to multiply some original equation. That in a verbose way is what we would be doing here. We're going to change the appearance, essentially eliminating denominators by use of the LCD, unique to the problem, the least common multiple of the denominators. All right? That's what the convenient expression in this particular case is going to be. This convenient expression is going to be an LCD for rational type problems, right? So to just sort of tweak this a little bit, what is going to be the original equation in this case is going to be an original rational equation, slightly more specific, okay? And I'm putting brackets here because you have to remember that the trick to this is you can get away with doing this as long as you do it to both sides of equals. So just maybe to help emphasize what the process is going to look like is an equal sign to make it look like an equation. You're going to figure out what the LCD is. You're going to multiply the left side of equals, and then to make it legal, you're going to do the exact same thing to the opposite side, the right side of equals. Right? The distributive property, essentially. Now, how to actually get the LCD, right? I'm going to refer to one of my documents again. Right, so let me turn the projector back on. Burn this poor bulb out. Uh-oh. back up, there you go. And if you have this printed, there's really one point of this. This is good information to keep because it's always true. But when you're looking for a least common multiple, and that is essentially what the lowest common denominator would be, there's the numbers portion of it, and then there's the letters portion of it. Right? The numbers, you would do it, if you're doing it by hand, the most brute force way would be to list the actual numbers as multiples. Remember, multiples are products, so it's like counting by, say, fives, 5, 10, 15, 20, something like that. And then whatever the other number is, if you're counting by 10s, 10, 20, 30, 40, 50, so forth, and then looking for the first match, all right? That's very brute force. There's a more sophisticated method you may or may not remember, which involves the prime factorizations. This is more akin to what you'll need to be doing in this class, all right? If you're just looking for the number, all right, you could use your calculator. There's a button on your calculator that's labeled math. You press that and then scroll over to the number option and then go down the list. What you should see is LCM in the style of a function, all right? If you're just comparing two numbers, then you would type LCM, whatever the first number is, hit a comma, whatever the second number is, and then close it. And then it will spit out what the numbers would be. All right? If you're dealing with three numbers at the same time, all right, then it's a little bit more annoying, but you have to sort of embed the function in the function. So you would get the function written once inside of itself, all right, and then hit a comma and then put the third number after that. All right? That should do it for three things at least. All right. What I want you to pay attention to from this diagram is essentially this. The letters portion of this, or if you have something slightly more complicated, that is an algebraic expression where there may be a number and then a letter next to it, right? Or some combination of them, plus or minus. Like you have a term, and then a second term. You just want to pay attention to this much of it, all right? You want the highest power of each unique letter or factor, all right? When you get denominators, what will be practical is to immediately draw parentheses around each of the denominators to make them an autonomous little factor, all right? And then analyze what the degrees would be, all right? Anyhow, you would want the highest power, that's the highest number that is in superscript, all right? Essentially, all right? The whole thing is the power of the base, so I should be more precise. But you're going to be staring at the exponents, all right? The highest power of each unique letter or factor, all right? Take this much information from this sheet, all right? All right, now let's do an example, all right? Now we'll turn this off again. And I think because I need light, I'm going to put the kitchen light back on. During the day, you have to fight the sun. At night, you have to fight the moon, I guess. With a lack of the sun, at least. Looks like a jelly bean. All right. So here, where you put in this situation where you would have to solve an algebraic, and again, you see that instruction, they don't need to tell you anything else. You're going to be employing opposite operations at some point, usually last. But if you had something like this, a rational expression, all right, minus a second rational expression, 3x, is equal to a rational expression 22 over 3, all right? This is, again, the more complicated type than just simply a fraction-esque looking thing set equal to a second one, all right? In that case, you would cross multiply. When you have a second term here, all right, you employ the more sophisticated technique, which is, again, all right, we need to have an LCD, and we're going to multiply by, all right, whatever the original equation is, all right? How are we going to identify the LCD, all right? Again, zero in on all of these denominators, all right? You could do this in two parts. You could say, all right, what is the LCM of the numbers, right? and then figure out what the LCM is of the letters, right? The more brute force way of figuring out LCM, i.e. LCDs, when it comes to the numbers is pretty easy because the numbers are small. So if you were counting by 2s and you were counting by 3s, what would be the first thing that matches? That is when you count 2, 4, 6, 8, or 3, 6, 9, 12, you know your multiplication tables. The number in this scenario would be 6, right? But now as far as the letters are concerned, remember that statement from earlier. You want the highest power of each unique letter or factor. So if the letter that we're considering now is degree 1 and this is a degree 1, there's not much of a trade-off there. There's nothing to compare. They're the same. So we want one of every type. So it's just going to be x in this case. Then we pair them together. That's the LCD. Okay. So in this place, to fill out my skeleton, I'm going to put 6x, and I'll just put a dot here to replace that. The original expression is what's still there, all right, 7 over 2x, minus 5 over 3x is equal to 22 over 3, all right? Because we have strategically chosen this convenient figure, the LCD of this particular problem, all right, what happens when you distribute it, right, systematically to each of these terms, and that's what makes it legal, whatever you do to the left or the right, everything is fair and square, right, is that there's going to be a cancellation effect of the denominators. All of the denominators are going away, they're eliminated. There's going to be, with varying, effect, some leftover components though, right? So what I like to do is I will sort of write a little reminder to myself as I go through it, all right? If essentially what is happening when you have 6x times 6x over 1, just to make it look like a fraction, 7 over 2x, the 2 would cancel and this would be left as a 3, and the x's would go away. So the entire bottom here would cancel. That's on purpose, all right? For the sake of not drawing the minutia every time, some of this is in my head, all right? What would be left over in this case is there's going to be 3 times 7. So I will write myself a little visual aid like that, all right? Next one, when you apply 6x to this, again, that's the effect. The entire bottom is going away no matter what. What would be left over in that case would be a 2, so it would be 2 times 5, all right? Last one over here, which again makes it legal, would, again, the entire denominator, if you've chosen the correct LCD, will go away. It'd be a 1, a 1, and a 1. But in this case, the letter wouldn't cancel, so you'd be left with 2 times, 2x rather, right, times whatever is there. That means that after all is said and done, you have this now. You have 21 minus 10 is equal to 2 times 22 would be 44x, all right? This does not look anything like the original thing, granted, but it is totally fair and square, all right? Why? Because of the consistency. If you've done it to the left and you've done it to the right, everything is balanced, even if it seems cuckoo that you just pulled 6x out of midair. It's fine, all right? Now you have a more or less a linear equation, all right? So combine what you can on the left, simplify, before, that is, apply arithmetic before you apply algebra. So what would happen here is that you would end up with just 11, right? And over here you'd have 44 over x, right? Now the letter is on the right side of the equals, but it doesn't matter, all right? Just realize that these are 2 parts, a coefficient and a variable pressed together, so they're understood as being multiplied. And if you want to justify moving 44 now from here to there, you would divide by 44, right? There's a cancellation effect, it simplifies really. And you would have x is equal to 11 over 44, which is the same thing really as saying 1 over 4. Right? X is equal to 1 over 4. Right? Now, I would be remiss if I didn't mention something here. This is legal, all right? But when you start to manipulate the appearance of an equation, by moving the variable either around via multiplying or dividing. There is the potential for an extraneous solution. So what you should look for is, once you have the simplified answer, you should plug it back in here, all right, to see that everything is legit, right? If you get some answer that doesn't work out, don't automatically reproach yourself. It could just be that it's an extraneous solution. It's not that you did something wrong. Your arithmetic could be fine, your algebra could be fine, but you end up with a dud for an answer. That's because we've gone through sort of the extreme measure of manipulating via moving the variable. Normally we don't move variables, right? Not via multiplication, not via division. When you do that, there's the potential. So do check, right? Check for extraneous solutions. All right, I'm not going to do that now because my video will be 800 hours long. All right, essentially duds that are not your fault. They arise from multiplying or dividing by a variable, right, which is not normal, right? Legal, but not a typical thing. They're duds, right? All right. I can tell you, because I did check before I did this, that you'd get 22 over 3 equals 22 over 3, so it's okay. All right. All right, let me do another one that's slightly uglier. Suppose you had something like this where the denominators are slightly more complex. They're a binomial as opposed to just a monomial. Minus a half. Okay. Now again, the habit that I want you to sort of condition yourself to get into is, if you're going to pull the trick, if you're going to eliminate the denominators, all right? Wrap a little parentheses around each of these, right? That makes this a factor, and in theory a factor. Why? Because we would multiply them together anyhow, right? We want, for the sake of having an LCD that we would multiply the equation by, we want the highest available power of each unique factor or letter, all right, if it was just a letter, but that would technically be a factor as well. All right, so if in this case the bottom factor is just x minus 3, it's degree 1, right? There's nothing there to begin with. Same thing here, it's just degree 1, right? And 2 is 2. All right, in this case, all right, we can't compare just a regular ordinary number that is a coefficient like 2 and 3 from the last problem, even brute force, to get it to be 6. So we're going to sort of fall back on this truth here. We want the highest available power of each unique thing, all right? So just take one of each unique thing. So if you have a factor of 2, that's going to be the thing that is part of the LCD, even if it's ugly, all right? What's the other unique thing? Well, there's 2 incarnations of x minus 3 that are degree 1, all right? So I'm going to have to include that, all right? If there were the situation where this was a 2 here instead of just 1s and 1s, then you would opt for that one instead, all right? But that's not the way that this works out, okay? So that, even though it's not especially satisfying, 2 parentheses times x minus 3, that's the LCD. It's not a warm fuzzy number, but that's what it would be. We're going to multiply it by the junk that is here. So if you have x minus 3, right, equals 5 over x minus 3 minus 1/2. All right, again, the trick to changing the appearance of this to make it equivalent, all right, legally, is to distribute the outside thing to each of the inside contents, both sides of equals. Right? Looks like a range war going on here, right? All right, now, very strategically, what's going to happen when you apply this, which is basically a numerator, if you wanted to put a 1 under it and then explore the fine details of this ratio times that ratio, that's cool. All right, I don't want to talk you out of it, but for the sake of timeliness, I'm going to do some of this efficiently. All right, the effect, if you've chosen the correct LCD, is that this is strategically going away, all of them. All right, what is going to be left over here, here, and here to multiply by will vary, though. All right, so if the factor that is x minus 3 is what was here, then what you have left over would be 2 times x. And the same thing here, you're just going to have 2 times 5 in this case. When you get to the half, it's the 2 that would be eliminated, and it would be the factor x minus 3 that would be left over. All right. Clean it up, that is, you simplify it, right, via arithmetic always first, right, which means that this is just 2 times x equals 2 times 5 is 10, right? And then it essentially would be -1 times x minus 3. So I'm going to start by putting -1 times x minus 3 just to make it really super clear, all right? The effect is that when you distribute this -1, and you should automatically group the sign that is adjacent here with that 1, all right? That's just going to change the signs of these things, all right, to eliminate this parentheses entirely now. All right, that means that you have 2x is equal to 10 minus x, 1x if you like to have the 1, and then plus 3 would be left over. All right. Again, you simplify the two sides of equals independently of each other before you begin doing algebra. All right. So that would require me to combine the 10 and the 3. And that would make this now 2x is equal to -1x plus 13. Right, now I'm a little short on space, so I'm going to kind of like tuck myself in the corner here. That means that if I have this, 2x is equal to -1x plus 13, and I build myself a little table, as I'm inclined to do. I'm going to move -1x from here to here, just because I like to have letters on the left. All right, and add it, cancels, add it, and this amplifies in this case. So you get 1 plus 2 is 3x, right, and that's 13 left over. Last step is to divide by 3 to move the 3 back. And then you have this, x is equal to 13 over 3. Provided that is simplified, and it is, that is your answer. Right. Again, improper fractions, even though they're kind of complicated in ordinary human conversations, are preferred in math world. Right? Why? Because if you plug this back in, rather than use a decimal, even the mixed number, it makes it easier to simplify. All right. All right. Now, if you had problems that were, again, even further uglier still, all right, that was a trinomial here, say, all right. That's the only reason why I mentioned this at all, right? Because there's so much stuffed into this one section, I don't want to bother. All right, you may have to factor first. So if you have to factor an ugly trinomial here, rely on techniques that are factoring techniques. All right. Okay, so that's another handout. All right. Here is just the other situation where you have basically a proportion equation. And then we'll get into graphing. 45. Okay. So if you had to solve, say, 3 over x minus 6 is equal to 5 over x. This is a glorified proportion equation. It is rational because notice where the variable is, it's in the denominator. But the technique is cross multiplication. Right? It's much easier than what we had to worry about at LCD. I mean, you could employ the technique of using the LCD would be x times the factor x minus 6, and it would simplify. But what's easier still is just simply to cross multiply. If it's just one fraction-esque looking thing on the left and one fraction-esque looking thing on the right, a ratio and a ratio, then all you have to do is multiply diagonally like this and this. All right, and then express the outcomes here. 3 times x abbreviated would simply be 3x on one side of equals. And then, just for the sake of clarity, this would be 5 times the quantity x minus 6 on the opposite side. Then you clean it up as best you can. Again, you perform the arithmetic, all right, before you perform the algebra, which is moving things over equals. All right, so if you have 3x is equal to 5x minus 30, look what happens. You end up with variables on opposite sides, so you could put the 3 here and then move the 30. I think it's less work if you just move the 5. So there's more than one way to do it. All right, I prefer to do it this way. I'm going to take the entire term, which is a positive, understood that way if you don't see a sign, and then via adding or subtracting, it takes the whole chunk. Moving it over equals would entail subtracting it. So I'm going to put it here underneath its buddy. I don't know what x is granted, but by sheer logic alone, something minus itself is 0. So it strategically cancels. There's a minus 30 here. And then you combine this. This is a positive 3 and a minus 5, so you get a negative 2x. And simplify by moving negative 2 back. This simplifies and that simplifies. X is equal to positive 15. Okay. Let me put my projector back on. Okay. There's that worksheet, as I mentioned. Just to give you some kind of level of comfort. I think, especially in the United States, we kind of, reproach ourselves would be the best way to say it, unnecessarily so. Right? You get mad, you go, oh geez, I'm stupid. No, you don't assume that. All right? You could do everything right and still get a dud for an answer, right? If it happens to be extraneous, right? Or there's even worse. There's names for these weird cases. What happens when solving equations? There are 3 possible outcomes, basically. I'm going to hit my light off again. I'll get dark. Okay. All right. There's a situation where everything goes according to plan. All right. You do everything right? And what you're hoping will happen, which is that its letter equals number, does happen. So say for example, you got x is equal to 5. The satisfying brainwashed way that we are taught to look for things, right? Letter equals number. That's more or less the normal situation, but there's a fancier word for that. That is called conditional. This is a conditional equation that produces that sort of a result, all right? Then there's these other 2 scenarios, all right? When you're solving equations and something weird happens, so for lack of a better phrase, I put weird case number 1 and weird case number 2. There are names for those which I want to give you. That's why I left it blank, because I want you to write it. But to generalize, here's how that would look. The first, and this is the more upsetting, is you get a number equals a totally different number, which is, just absolutely not true, and it should have a not equals slash, no smoking slash through it, all right? This can happen even if you've done everything right, all right? Even if all of your arithmetic is good, even if all of your algebra is flawless. There are some problems that produces the result, when you're checking for extraneous solutions, for example, right? Say you are checking extraneous solutions for, all right? Again, don't automatically reproach yourself. You may not have done anything wrong. It's just that you got a dud in extraneous solution, all right? That would be a situation like this, like, 2 equals negative 9, all right? That's baloney, all right? Something can't equal something totally different, all right? They're not comparing a letter. You're comparing concretely known numbers to each other, all right? The name for that is a contradiction, right? Or in some cases that they might call it an inconsistent equation. Right, this is more theory than it is you know, a technique. Okay, an inconsistent equation. All right. It happens sometimes. Then there's this situation. Something weird happens, but it isn't untrue. This is false, right? This is just completely false, all right? This down here would be true if you have, you know, a letter equals itself, like x equals x. This is weird, right? Or a number equals itself. Let's just say it's 7 equals 7. All right? It's not giving you some untruth. There's no fallacy there, all right? But it is unexpected, all right? In a situation like that, what you would refer to this a little bit more officially would be to call this an identity. All right. All right. It's an identity equation, right? All right. Where it would be true for all situations, all right? This is something that arises very often when you have a system of equations. All right. In terms of the number of solutions, right, in a situation like this, the fancy way of presenting the answer would be to put it in fancy braces like that. You just put the number inside. If you had a situation where you have a contradiction, right, the general way of implying that there's a contradiction in terms of the number of solutions would be to put either fancy braces, just simply empty, or you could use this no smoking crossout, which is known as null. All right, it's the empty set, or it's null. You could use null. Just don't put that symbol inside there because it looks like a 0, and it isn't. That's the reason why it's stylized as it is, that the line goes through the loop, the hole. If you have an identity in terms of the solutions, anything that you plug in would end up being balanced. So in this instance, all right, the fancy way of writing the answer would be this sort of Great Gatsby-esque style R, right, for all real solutions are possible. Okay, so that's an infinite amount versus a finite amount, or nothing at all, right? Okay, so a little bit of theory. All right, now we get into graphing. I don't know why they put this together in the same chapter, but hey, whatever, right? Here's an overview of graphing. There are at least 4 techniques. Well, there's 3 main techniques. Let me get rid of this schmutz here. There is, and I like to teach it, that when I teach algebra, I get such joy out of it, because although this is the one that you want to really zero in on for our purposes, this is relevant to us. Technique number 3, reading something in the slope-intercept form, right? There's a lot of nuance to it. It's a lot of skill, a lot of prerequisite knowledge that a person would need to know in order to get to graph something with that, all right? Otherwise, they're using your calculator just by pressing 2 buttons. But there are these other techniques, all right? And they're valuable, but they're not really necessary right now. The most brute force way of drawing a picture of a line is to generate your own dots, your own coordinates. Like, I would recommend using this array of -2 to +2 because the numbers are small and they're easy to work with. Like 0 times anything is 0 and 1 times anything doesn't change anything, right? If you plug those into some unique equation, they'll spit out the y value, right, for x's. And then you pair them together and you have dots. You know, they produce coordinates that you can plot, all right? Slightly less brute force, but still, you know, doing things by hand would be using 0 strategically in 2 places, either as a y-intercept or an x-intercept, right? It's just plugging 0 in x versus plugging 0 in y, and then seeing what you get. Then you get 2 dots. If you're talking about a line, that's as many dots as you really need, all right? Anyhow, for our purposes, we need to know what the slope is, right? And what the y-intercept would be. That's just this weird label that we have for it, in English at least. B. Right? That's more or less the starting point, and then you use the slope to get an infinite number of points after the fact. You only just need 2. All right? So, let's talk about the slope. All right. There are potentially 4 different slopes. So here's another slide to summarize. I can't show you the whole thing at once, unfortunately, but there's 4. All right. Here are the sort of normal 2 that you're kind of hoping for. All right, which is that you have a positive slope. Now, if you have no numbers, but you have a drawing of a line and it's a diagonal line, all right, more or less in the orientation of running between what would be quadrant 1 and quadrant 3, then you could say with some certitude it's a positive. All right. We would like the slope, which is weirdly labeled m, to be some kind of a fraction, though. Why? Because that's the instruction of how you would actually incline. That's its job, right? This line. If instead you have a diagonal line that is running more or less from the 2nd quadrant down to the 4th, again, even if you don't know the numbers, you could say with some kind of certitude it's going to be negative, right? Negative whatever the fraction would end up being, all right? There's 2 other situations, though, all right? You could have a perfectly horizontal line, or you could have a vertical line. Now, somewhat ironically, when you have a vertical line, even though in ordinary conversation we'd say, wow, that's pretty steep. Like if you went up to the face of a mountain that went straight up, you go, wow, very steep. We think of slope as a measure of steepness, right? But when it comes to a perfectly vertical line, the slope is not actually defined. The reason for that is because of the arithmetic that would be involved, right? Essentially, when you calculate the slope using the formula, you would get 0 as a denominator, which is like dividing by 0, which you can't do mathematically. So we say it's an undefined slope. All right. If, on the other hand, you have a perfectly horizontal line, the way that the math would work out is that you get a 0 in the top. So that's dividing into 0 rather than dividing by 0. All right. There's no commutative property of division. The order definitely matters of arrangement. So horizontals are perfectly 0, right? Verticals are undefined, right? And here is the formula, all right? There's the fancy physics book way of looking at it, delta triangle, all right? Y over delta x. If you're not familiar, this is the logic. This is a Greek letter, delta, all right, which is translates to the letter D. D as in difference. All right, and that means subtract, all right, 2 things. So if you see delta y, it means subtract the y's. If you see delta x, it means subtract the x's. When you see these little subscripts here, they're not an exponent, they're just a label, so make that distinction, all right? They're just saying that there's 2 of these, this is the second one, this is the first one, this is the second one, this is the first one. Often what happens is they give you 2 sets of coordinates and you have to plug them into that, all right? So, here's an example. I think I might turn on the light now. Okay. Let me just pull up this graph paper. It's not going to be immediately necessary, but I want to show you how to do it 2 ways. Now in here. All right, if you had to calculate the slope, given 2 points, 2, -1 and -5, 3. Right? Do yourself the favor of labeling these x1 and y1 and x2 and y2. It doesn't matter which is which, but my logic is this shows up first, so this is x1 and this is y1. Right? They have to be the 1's together and the 2's together. So this will be x2 and this is y2. Right? Then you take them and you superimpose them on the formula. So if the slope formula is y sub 2 minus y sub 1 over x sub 2 minus x sub 1, you don't have to do this on graph paper, of course. You're going to insert strategically each of those values where they're supposed to be. All right. Let me do this first. I have a bootleg version of Paint here, so I'm just going to open it so that it's just white. Now, yeah, whatever. Cancel, huh? I wonder if they ever fixed that problem. I would like it to. All right. So if I've designated y2, 3, I'm going to write a 3 here. There happens to be a minus in the formula, to be careful of that, and then the y1 is -1. You have a double negative, which means that this is really 3 plus 1, which is a 4 on top. Right? In this case, if you put the x's in, this is -5, the way I've decided. There's a minus in the formula, and then there's a 2. Right? Same signs you actually add, you just amplify and get a bigger negative. So this will be -7. All right. Now do remember, when you have a fraction, even though it worked out this way, there's 2 ways you can write it. Textbooks have a tendency to just write the minus, the negative symbol, neither favoring the top nor the bottom. But when you're graphing, it would be to your advantage to put it one place or the other. All right. So if you felt like it, you could make this -4 over +7, or if you like, you could make it +4 over -7 like it was. All right. These are all the same thing. All right. But it's these two versions of it, the way that it came and a slightly arranged differently version of it, that would be practical if you had to graph something. All right. So let me put the graph paper back to show you how to do this sort of visually. All right. I need this space, so I'm going to clear this out. Let's say that you had graph paper, and you took the time to plot these coordinates, all right, and you would have, let's see, 2, -1, you'd have a dot here, and then -5 would be 1, 2, 3, 4, 5, and then up 3, 1, 2, 3, a dot there, all right. We already calculated the slope as -4 over 7. I'm going to put this here. All right. I like the negative on top, it's just kind of a preference. I know it's not written that way as it calculated, but that's legit. As long as one or the other is negative, it's the same slope. All right. Now, in theory, these would represent a line that would go through these 2 points. So if that were the case, all right, I'll just take this and draw a line through it, and attentively as I can, using the coordinates here. It's always good to overextend your line too, extrapolate. That's kind of the whole point of this in practical math, to make predictions either about the future or the past that is unseeable, or in between, interpolating. Right? Anyhow, if this is done on graph paper, the actual hand plotting, you can again pull that same trick, which is to draw a right triangle that connects these two. All right. So you got to be a little bit careful, but you want to draw a line that is up to just underneath the dot, and then a line like that, and then you have a right angle. How many squares tall is this? 4. All right. How many squares wide is this? 1, 2, 3, 4, 5, 6, 7, as predicted. 7. All right. This is essentially a delta y value, and this is essentially a delta x value. Right? The conditions of being a slope. All right. But just garnered via the the hand method, sort of by drawing it. All right. The only thing that you wouldn't get from doing this is whether it's a negative or a positive. All right. You can reason it through, all right, but do it as an afterthought. If the incline of this line is again running essentially from what would be the second quadrant down to the fourth quadrant, and it is inclined that way, then this would have to be a negative slope. All right, you can figure that out if you memorize some fun facts. All right, otherwise, think about reading things from left to right. If you start here, a slightly higher place, the high ground, and you go to here, the low ground, right, you're down 4, right? So this is down 4, all right? And then from there, if you head this way, you're going towards the right 7. Right? So there's more than one way to do it, all right? Now also, if you wanted to write the equation of the line at this point, you can. Just having those 2 points, you can use one or the other, and knowing this slope, you can then take advantage of something called the point slope formula, all right? You can write, if you don't remember, the equation of a line with just this information, all right? You know the slope, all right, because you had 2 points, all right? Then you take either one of them. Basically what you would do is you would plug them into this equation. Y minus y sub 1 equals m times x minus x sub 1. See if that's in view of the camera. It's a little faint because of the nature of this. So let me put my bootleg paint back. Yeah. It might be easier to see now. All right. Essentially, this is known as the point slope formula. When you have 2 dots, you want to use the point that is 2 ordered pairs here, 2 points. That's all you need in order to use this formula to write the equation of a line. Now, I didn't really ask you to do that, but we can. All right, and eventually maybe we will be. There's 3 voids that you're going to fill in: the y with the subscript, the x with the subscript, and the m value that we calculated. All right? So you would put essentially negative 4/7 here, and then take either one of these 2 points and plug them in y1 and x1. Does it have to be this particular dot versus that one? No, all right? But I would say use whatever is the smaller numbers or whatever works well with the denominator of 7. In this case, I'm just going to go with 2, -1. So that's an x, I would put a 2 here, and that's a y, so I put a -1 there. All right? For the sake of space, let me write this a little bit more cleanly over here. All right, the result is this, that you have y double negative, so it's +1, is equal to -4/7 times the quantity x minus 2. All right, you're going to get an ugly fraction in this case because of the way the numbers work out, but it's not too bad. All right. Simplify each side as best you can before you start rearranging the parts algebraically. The best you can do here is eliminate the parentheses by distributing. All right? Which you kind of wanted to happen anyway. All right? So in this instance, what would happen is that you would get -4/7 with an x attached to it. If you are inclined to write the fraction like this, -4/7, just realize that the x, is really attached to the top. Otherwise, it's just away from it. All right, don't ever put it on the bottom number. All right, then it would be a rational expression instead. Okay. If this is -4/7 times 2, that's like multiplying -4/7 times -2/1. Top times top, bottom times bottom. The effect is that this is a positive 8/7. All right, which may be kind of intimidating, but leave it alone. Over here, you still have y +1, all right? We've done the only thing we could do in this case, which is eliminate the parentheses. If you want to make this look a little bit more like, instead of the point slope formula, the slope-intercept version of this, all right? Then we want to move this 1 from here over to here, all right, underneath the 8/7. So you build a table, move this from here to where the other number is. All right, these are like terms. Justify that by opposite operations. So you're going to subtract in this case. And now you would subtract 1. Because you have a whole number and you have a fraction, what would be practical is to express that amount of 1 using that denominator, whatever it is. In this case, if it's 7, the equivalent of 1 whole is 7/7, so 7/7. All right? And now, since you have 1 of each sign, you're going to actually subtract. And all that it matters is that you're going to combine the tops. So 8 essentially -7, all right? That means that this is really y is equal to -4/7 x, all right? And that is at the location of +1/7. Right? In terms of the graph, all right, this would be the y-intercept, right? At the location of 0.17, which is a fraction and it's very puny, but that would be precise, that would be exact, that would be accurate. All right, this is the slope. All right. Okay. Gotta make one little correction. Okay. 7, 7, okay. All right. Now, let me give you another slide here to summarize some information. There are, where did we put that? Four styles of the line equation that you might see. All right, let me get the gobbledygook out of the way here. In your math life, not necessarily this chapter, but it would be good to be aware of them, you know, even if you don't use them. So here's the summarize, right? What is really relevant to us is this half of the diagram. Right? Let me turn this off again. Right. Good to recognize what would be the point-slope formula and the slope-intercept form of the line equation. You want to use these basically when you're doing section 2.2, right? Rather than 2.1. These other things exist though, right? If you were solving systems of equations, you would want to be familiar with something known as the standard form, all right? Don't be intimidated by these capital letters and that they're different from any other letters here, all right? In a textbook, when they use a capital letter, that's just to specify that there's something that you have to look at, all right? It doesn't mean that it's a different figure per se, all right? It's giving it a job, all right? It implies that they have to be whole numbers in this case, with the coefficients, and the A being up in the front should be a positive, ideally. There's the general form, which exists, nobody uses it, all right? There's the standard form, which is useful when you have to solve systems of equations. And, you know, if you were dealing with, you know, one or two equations at the same time, pardon me, two or more equations at the same time, and then this is when you're actually graphing. Pretty much you're going to start with this, and you're going to rearrange the guts to look like that, right? I know that there's two x's and two y's here, but it's these that have the subscripts that you actually fill with a number given those numbers, right, or determined, right? And you fill in whatever the slope is eventually too. If you compact it all together, it would be these three parts. That's just to generalize. B is the weird label for y-intercept. All right? It's like M is sort of a weird label for slope. I don't know why it chose a letter M. All right. Here is just a couple of examples. Yes. I'm in the dark. To show you how to do this, right? Is that visible? I think it's okay. Maybe put the kitchen light on again, because it's getting too dark. Here's an easy one. All right, if you were asked to find the equation of a line, given these conditions that m is equal to -3, and it passes through the point of 4, 8. All right. Again, start with the point slope formula. Y minus y sub 1 equals m times the quantity x minus x sub 1. All right. And just realize you're going to fill in this figure here, here, and here, right, with the information given to you. So remember, x is first and y is second, so I'll put subscripts. Right. You would stick an 8 here, and a 4 here, and -3 for this condition, and then clean it up. All right. it usually should specify, and I hate this, but they'll say, oh, put it in standard form. I would still start with this, all right? And then rearrange it if it has to be standard form so that the x and the y are on the left side together, all right? But that's an afterthought. Usually, in the more practical way, you would write this in the point slope formula, and then translate it into the slope-intercept form, right? Why? Because even if you were using your graphing calculator to graph something, there's a button on your calculator that's labeled y equals, so that you can enter something that's in the style of y equals whatever the equation is. It's a graph, and then you would graph it, okay? I don't know what I was doing when I had that. Anyhow, distribute, and you end up with y minus 8 is equal to negative 3x plus 12. All right. Again, build a little table. I'm going to move the 8 from here now over to there via opposite operation. There's a cancellation effect. Y would be equal to negative 3x plus 20. All right. Again, the practical information to glean from this is that if you had to do it by hand, this is the point 0, 20, right? And this being the slope would be 3 down from there, and then 1 to the right, ultimately. Because remember, if you have something that doesn't look like a fraction, negative 3, you could write it as negative 3 over positive 1, right? 3 down because it's negative, 1 to the right because that's what the denominator would have to be, all right? From that point, right? From here. Okay, 0, 20. Okay, the slightly more complicated problem would be if you were just given the points as I mentioned earlier, right? If you had something like this, 3, 4 and 0, negative 3, you're still going to try to use the point slope formula, and I would start with that, right? But you realize early on that there's some missing information, right? But don't get scared. I mean, you could figure it out. You have to. There's one thing I want to impart to you. If you learn nothing from my class, eventually you have to trust yourself that you can figure anything out, right? Y minus y sub 1 equals m times x minus x sub 1, all right? You have 2 points, all right? Which one is x1 and y1, all right? It doesn't matter which, right? You could use either one of these. But if you were to, let me just say hypothetically, I did this one and this one, all right? Just because it showed up in my face first, all right? Then immediately after you put a 4 here and a 3 here, you realize that you're missing m, all right? And you might go, ugh, all right? Well, all that means is that essentially is that you have to calculate the slope as we had done earlier. That's a 2, all right? So now you're going to incorporate these 2 numbers anyway. So just to complete this thought, if this is x2 and this is y2, all right? If I put them in here appropriately, it would be negative 3 minus, because of the formula, 4, which makes it negative 7 again. And then 0 minus 3 would be 3, so positive 3 in the bottom in this case. Right? That makes this negative 7 over 3 here. Right? Now you have all the information you need. Distribute to clean it up. The 3's are going to cancel in one case. All right, what does that mean? It means that this is going to be y minus 4 is equal to negative 7/3 x, big X, just not to, don't attach it to the bottom. And then the 3's would cancel and you'd be left with positive 7 in this case. Okay. Oh, wait. Ding dong. Oh yeah, sorry. 0 minus 3 is negative also, so this becomes positive. All right. This is a positive 7/3, which means the positive times the negative that's here would make this, sorry, negative 7. Okay. All right, and that's a positive. Okay. So again, now you just build a table. Move 4 via opposite operation. It cancels here. Y would be equal to 7/3 for the slope, x minus 3. All right. Again, if you had to plot this by hand, that's the ordered pair 0, -3, where you would start, and this would be 7 up and 3 to the right. All right, because of the nature of being positive over positive. Okay. Let me put my projector back on. Okay. Wake up, please. Okay. Okay, as I said, this is the best tool that you have. All right, this is usually what you would convert it into. Even if you were using your calculator, you would want to graph, you'd want something in this form, the slope-intercept form. These are things that exist. All right. Now, if you had to write equations, just so you are aware, all right, here's 3 possibilities. All right. When you have diagonal lines, they're the most complicated. All right, there'd be the y equals mx plus b version. If you had to write an equation that is representing a horizontal line or a vertical line, it's a lot less complicated. It's more simplified. All right. In the case of a horizontal line, the equation would simplify to just simply y equals a number. All right. Whatever the whatever the y-intercept is, that's what the equation would be. Y equals whatever b is. Remember why? Because the slope would be 0 for a horizontal line, so we'd cancel this term anyway. All right? In the case of vertical lines, because slopes are not defined in the case of a perfectly vertical line, the equation would simplify to whatever the x value is, right? The x-intercept, where the line would be crossing the x-axis. All right? And in that case, it's just whatever the x component would be of the ordered pair. All right? So these would be easier equations to write, right? All right, now here's pretty much the last thing, all right? There's 2 line relationships that would be good to know. I'm gonna opt for this slide because I think it's better. Here's a little reminder in the thought balloon. Use the point slope formula to convert to a slope-intercept form, all right? If you have 2 lines on the same graph, all right, potentially one of 2 things will happen. Either the lines are going to cross somehow, or they're never going to cross. All right. If the lines cross, they may cross just randomly at whatever angle that they do. All right. In that case, we would just call them intersecting lines, and that would be the symbolic representation of them, like an X. All right. If they happen to cross exactly at a right angle, all right, 90 degrees, all right, then we would refer to them as perpendicular, and this is the symbol to represent them, all right, a T shape, more or less, upside down. If the lines never cross, then we would call them parallel. If they never do this at any point in their movement into infinity, then they're 2 forward slashes, essentially, is the abbreviation. All right, now, the minutia is this, all right, the perpendicular lines would have opposite sign reciprocal fraction slopes. All right, the abbreviation for that is this thought balloon here. The second slope would be the first slope as a reciprocal, all right, and then a different sign. If it was positive, it would be negative. If it was negative, it would be positive. All right. If the lines are parallel, they have to be exactly the same slopes. Right. The only other condition that is a given is that they have to have different y-intercepts. So the b values, they have to be different numbers. They're not equal. Because if they're exactly the same, then they overlap and they're not technically parallel. They're touching everywhere rather than nowhere. Okay? So, here is an algebraic way of proving that you have perpendicular lines. All right? If you examine the slope of the first and the slope of the second and multiply them, and the result is -1, then you could say with algebraic certitude, they didn't even draw anything, that they are in fact this situation, perpendicular. All right, so just that's a nice time-saving device. Okay. Here's this last thought. Crossing lines generally, meaning either of these situations, all right, may coincidentally have the same b value, they may have the same y-intercepts, but it isn't mandatory. Right? If they do, great. If they don't, then that doesn't matter. Right? All right. Here's the last two examples. The last one, I think. And then I'll stop. Getting scratchy. Yeah, that's it. Okay. Suppose you were tasked with writing the equation of a line that is parallel to this. 5x plus 3y equals 1, and it passes through this point, 3, 5. All right, you are still nonetheless going to start with the point slope formula and then rearrange it to create write the equation line. That's the ideal situation, whether they specify or not. All right, I'm going to turn off the projector now because it's kind of in the way. All right, and maybe you put the line on. That sort of helps. Okay. Okay. Just to flash it really quickly, notice what was given to you in a case like this. Right? This is which type or which incarnation of the line equation. This most closely resembles what would be technically the standard form. It would be good to know how to recognize it as the thing where the x's and the y's are on the same side of equals. All right, but the other more stricter condition is that these are whole numbers here. Right, as coefficients, and the lead one is a positive. Anyhow, you want to rearrange this to get what little information that you can out of it. Right. So here what you would do is take this and rearrange to slope-intercept form. Why? Because even if we want something that's parallel, we would need to pluck out the slope from that. So if we do that, 5x plus 3y equals 1. All right, I'm going to strategically rearrange the parts by moving this term 5x over to here. Right. It is understood as being a positive, so to justify taking the whole kit and caboodle, the number and the letter at the same time, I'm going to just add a subtract. In this case, it would be subtracting. And I have nothing to combine it with, so I'm just going to park it over here. All right. There's going to be strategically a cancellation effect here. What is left over is simply 3y. And then, because I want it to conform to the slope, not the slop, the slope-intercept, I'm going to put this in the front. It doesn't have to be, but it would be more better etiquette, shall we say. So minus 5x, and then this is a plus 1 is going to be here. All right. Last thing is to move the 3. So if the coefficient is 3 to justify moving it, remember it's got to go to both pieces, right? Not just, you want to put it on the opposite side, but not just one thing in lieu of the other. You want to do both of these get a 3 under them, all right? There's a cancellation effect essentially, and then that means this is y equals -5 over 3 with an x attached to it, plus 1/3. Okay. That much information is great. Now, if we're going to create from scratch a parallel line to that, it would be in this form of this that we would be able to do that. All right. So here is again the point slope formula to accomplish this. So I'm going to take the points that they've required, passes through x1, y1, 3, 5, and then I'm just going to erase this because it's getting a little too messy. Write 5 here and a 3 here, and borrow this because it has to be parallel. We're going to use exactly the same slope. So minus 5 over 3. Right? I'm going to distribute that. The effect is that this becomes y minus 5 is equal to negative 5 over 3 with an x attached to it, and then when you distribute negative 5/3 to that 3, it becomes positive, and the 3's cancel, leaving you with just 5. Right. Then build the table, move the 5, which coincidentally is the same number here and here. That cancels. Y that would be parallel would have the same slope, so it's negative 5 over 3x plus 10. Parallel lines have the same slopes, but different intercepts, y-intercepts. Okay? All right, and that's everything. Let me just remind you about the homework here. All right, the good news is that the MyOpenMath software is functional. I tested it myself today. I did the intro. I would do the intro for your own sake. All right, so the reason is because the software is very particular how it likes you to enter information. So the whole point of the intro is to acclimate you to how it wants you to type. All right. If you're not aware, you may type something correctly and it will mark you wrong. So do yourself a favor. All right. For homework, all right, at this point, right, do the intro to MOM in assignments, and this is in Canvas, of course. All right. First and foremost is, again, this will explain how to enter answers, all right, into the software, MyOpenMath. All right, you definitely want to do that. We just covered section 2.2, we, the royal we. All right, so at this point it is safe to do section 2.1 practice. I'm going to eliminate the other things. And then 3, do section 2.2 practice. Right, they're a bit involved, so do them. Don't do them in one sitting. All right, just do one or the other in one sitting because it's about an hour of your life. All right, all right. So I'm gonna make them do probably. I gotta look at it. At the end of the semester. Do not wait, please God. Do not wait until the last day. All right, to go. I gotta do all this homework, because there's no way in hell that that's gonna work. Okay, please. All right, I just want you to have a sufficient amount of time because the exposure, the experience is really what you're here for. If you do these homework problems, if you do enough of them, you'll learn it. Anybody will. All right, I got dirt on my head like it's Ash Wednesday. All right, anyhow, I'm going to set them as they occur, the forthcoming practices, the homework, all right, piece by piece, all right? But the end date for all of them should be towards the end of the semester, okay? Right. Do at the end, but don't wait. Start immediately. All right. Okay. So I want you to have the time to think about these things because, again, otherwise, what's the point? All right. Try to finish one section at a time. All right. I don't know if it will give you credit if you just walk away. I wouldn't take that risk myself. Okay. All right, thank you guys for listening. I will communicate again on Thursday. This is for Wednesday. Careful out there.